Okay, thanks to the organizers who gave me this chance to do a presentation. Today, our topic is characterization of domains by automorphism groups. What do I mean by automorphism groups? Automorphism groups is all of the, suppose you have a domain omega, and you have all of by holomorphism from omega back itself onto omega itself, and automorphism group contains all of such automorphism, biholomorphic automorphism. So there is a very classical famous theorem by Cartan. He said that if omega is in several, if omega is bounded, then the automorphism group is a Lie group, and okay, let's continue. So firstly, let's compare what happens for first dimensional and higher dimensional, because in first dimensional, it has been done principally because the Riemann mapping theorem. In first, so let's see the. Today we're going to just focus on simply connected bounded domain. Firstly, so for one dimensional, it means C1. In C1, the model domain is going to be just a unit disk because of Riemann mapping theorem. And for higher dimension, the model domain is unknown because there's no Riemann mapping theorem. We have a lot of modern domains. So for automorphism, okay, we are going to ask, is automorphism group compact? For the first dimension, if you study first dimensional case on the unit disk, you will find that all of automorphism group is just a Mobius transform. So the answer is no. You can always bring an interior point by a family of Mobius transform to the boundary, smooth boundary. But for the higher dimension, it is possible that automorphism group of omega is compact. For example, such this one ZW. Let's just consider in C2 this domain. Now let omega equals to that z square z to the fourth plus w to the fourth smaller than 1. So this domain gonna give you compact automorphism groups. That means you take arbitrarily many automorphism on this domain, and we'll find the limit will still automorphism. You cannot bring a point to the boundary. This is quite different with the first variable, first dimensional case. Also, can automorphism group in several complex variables be non-compact? The answer is also yes. Okay, one easiest one for smooth boundary is just a unit ball. Right, this is well known, and the automorphism is quite similar to the Mobius transform. So in higher dimensional, the automorphism group could be compact and could be non-compact, which is different. And there is a famous theorem. What do I mean by accumulation to strongly pseudo-convex points? That means if you have an interior point Q and if you have a boundary point P, such that there is a sequence of Fi which inside automorphism group, then Fi Q gonna bring your interior point Q to the P as I goes to infinity. This what do I mean by accumulation to P. If P is strongly pseudo-convex, there is a very famous theorem called the Wang-Rosset theorem, which said actually this domain omega, if this happens and P is strongly pseudo-convex, this domain gonna be just biholomorphic to the ball, unit ball. And also, by Cartan theorem, okay, if you study the what do I mean by the accumulation points? Actually, what I mean is this. Okay, same setting. If you let Fi be in a sequence in automorphism group, and Fi bring an interior point Q to P, we consider the limit of Fi. But since we want to study the limit, so by Montel theorem, the subsequence must have a limit. So we may pass it to a subsequence. We consider the limit. The limit is gonna be a map, and we start the image of the limit of the limit map. It will contain in boundary of omega. This is what proved in Catan's theorem. And okay, there is a natural question. Since we know the limit, the image of the limit map is contained in the boundary, how about the limit of F inverse I? Maybe passing to a subsequence. But inverse is also an automorphism because Fi is automorphism, so Fi inverse is an automorphism. What's the image of that? It will also contain in partial omega, boundary of omega. This is quite new result. And you can check Mobius transform. You will see the same thing holds for one-dimensional case. So in some respect, they are quite close, but some respects they are not between the one-dimensional and the higher dimensional. Okay, but we are not going to talk about all of the results there. We're going to talk about mainly two results, but the second result, since I don't have a lot of time, I will just show you, and if you want, we can discuss it later. So we mainly focus on the first result. Why do we consider the first result? We start from here. So theorem is, I think this proved in 1990s by Greeny and Crane. If omega is a boundary domain with smooth boundary, assume there is an interior point Q, same thing. And you have an Fi, which are in the automorphism group, bring the Q to the P in sense of limit. Then what is going to happen is P is not contained in holomorphic hood of omega, or holomorphic hole. I don't know the pronunciation. So what this means, this conclusion is equivalent to say there is a holomorphic function. There exists a holomorphic function locally around P. That means you can find a neighborhood of P, and you consider locally this shadow region. And there is a well-defined holomorphic function defined here, such that this function, holomorphic function, cannot extend beyond your point P. Okay, of course, this case contains strongly through convex. But if P is strongly through convex, then it's biholomorphic to a ball. This theorem also equivalent to say P is a weakly through convex point. So might be strongly through convex point, maybe just through convex point, but not strongly. And okay, to give a name, we call P is orbit accumulation point, and we want to classify it a little bit. We also consider Fj inverse. If Fj inverse bring your Q to a boundary point P tilde, if P tilde is different with your P, then we call it hyperbolic accumulation point. If unfortunately your P tilde is the same as your P, then we call it parabolic orbit accumulation point. Okay, I think yeah, let's go on. So what is the questions? From this theorem, there is a very natural question arises. We know the P property of the P But how about the global property of the whole omega? This is possible because generally speaking, your omega j is going to bring a very large stuff close to your limit point P. So we might get some result of the boundary, the global boundary property of the omega. Okay, let's try to look up a previous result. Okay, there is a good news when I find the paper by Bedford Pinchuk. They have a lot of a few papers together. In C2, if your boundary is assumed to be real analytic, then actually they can prove a more general theorem. If the boundary is assumed to be real analytic, then the omega is globally pseudo-convex. Okay, this is very good and it's very exciting. But after that, I found the bad news because when you read the proof, you find they use quite a lot of Siegel variety, which is not suitable for our case. Because we just want to consider the smooth boundary case, not real analytic. So that means we need to figure out some. We need to have some new idea and some new technique. There's a theorem about that positive result. If we assume, okay, omega in C2 is a bounded domain with smooth boundary of finite type, suppose Bergman kernel can extend to the boundary except for the diagonal sides, then as a locally bounded function, then P, and we also assume P is a hyperbolic orbit accumulation point. What is going to happen? That omega is globally pseudo-convex. Okay, several remarks. Firstly, this confirms our guess in case of a non-parabolic accumulation point in C2. Why do we say the hyperbolic? Why is non-parabolic? Because by previous this property, we can say if a boundary is assumed to be finite type, then if the point is not hyperbolic, it must be a parabolic accumulation point. Where am I? Yes, here. So if you just need to find a subsequence of your fj, which is not parabolic, then you can repeat the theorem and get the whole the global property of this domain. Okay, this result is also holds for a higher dimension, but we're gonna just chase for the idea, so we're gonna just treat it as in C2 today. Why do we assume hyperbolic? Because in 2012, Kim Song-Yang improved a theorem she also used hyperbolic, and this theorem tells us in exactly the same setting of previous theorem, the defining function is a v smaller than p z bar, where p is a homogeneous polynomial. Note we write that z equals to x plus iy and w equals to u plus iv because it's in C2. So this okay, we're gonna just use this nice defining function because in this case we have v equals to a homogeneous polynomial of z, and which is very nice. There is a lemma. Okay, we can call it a fact. There's a fact which is very useful, but also very easy to prove. If your defining function, well, why this defining function is nice? Because if you want to study pseudo-convex or pseudo-concave, you can just study the defining function. And for this defining function, you will see the pseudo-convexity is just determined by the argument of the first variables. If you write the, you can prove it. This is not hard. And okay, I will explain it on the board. What this means. By the way, I cannot draw a graph on C2, I can just draw a graph in Z-plane. Consider our board is a Z-plane. And this is locally around P, and I also call P 0. So this is a Z-plane. What this means, this is the projection of your boundary onto Z-plane, okay? So this, I can have a lot of sector. And since the pseudo-convex is just determined by argument of Z, so it happens like this. For example, this sector could be strongly pseudo-convex, but this sector is strongly pseudo-concave. This sector is also strongly pseudo-concave, but this sector is also strongly pseudo-convex. What do I mean by this sector is strongly pseudo-convex? That means the inverse of this projection of this sector is strongly pseudo-convex. The inverse projection of this piece is strongly pseudo-concave. Concave, yes. So this might be strongly pseudo-concave. This is also strongly pseudo-concave. So, but it has a lot of it have three possibility. For example, can we have all of P be strongly pseudo-convex? If this happens, okay, we need some step to do. But intuitively, you can, since you Fj map a point far away to very close to your P, your accumulation point, and since if this is a strongly if this is a pseudo-convex piece, and Pj gonna bring a point far away or around 0, and since it preserves the pseudo-convexity, so the far away point is gonna be pseudo-convex. So this is not hard. This is intuitively, but if you want to write it in detail, we have to use we have to do some work, but not much. Okay, it also has the case if each sector are pseudo-concave. If this happens, again, intuitively, I cannot go in detail. Intuitively, the holomorphic CR function, we're going to borrow CR function, the concept of CR geometry. CR function inside, which is defined around this neighborhood, going to extend outside. But and this contradicts with Green-Kranz observation theorem, the first theorem I have ever showed. I call it Green-Kranz observation theorem. So this cannot happen because the Green-Kranz observation theorem. So there is no trouble. But for the third case, if there is a one pseudo-convex piece and also one pseudo-concave piece, what is going to happen? Okay, this is what we are going mainly to talk about, the idea. Okay, if this happens, we give a proposition which saying that if this happens, the CR function defined around your P gonna extend to both sides. Okay, if we have this proposition, we're gonna have applying this proposition to the third case, again by Green-Kranz observation theorem, this cannot happen. But why this proposition happened? This is I don't have much time. I will just talk about the idea. When should I finish? I miss 5 minutes. Okay. I see. Okay. Okay. This. It's a typo. No, there's a typo, or because I have a. It was supposed to be a 15-minute talk. Okay, but I okay. So. If you can wrap it up soon, that would be nice. All right. Okay. So. Okay. This is. I will say this by Bishop equation and the exist vector, and you can see if, okay, let's mainly do the pseudo-convex part, pseudo-convex, and the pseudo-concave are going to be similar to this case. I will prove if the boundary admits a pseudo-convex piece, then the exist vector gonna point inside. That means point inside of the omega. It means the CR function gonna extend to inside. But with the other piece, a pseudo-concave piece, the exist vector gonna point out. That means CR function gonna extend to outside. So the CR function gonna extend to both sides. So we mainly just do this. Oh, okay. I will tell you the difficulty. Very natural idea how to settle down this is you have a lot of analytic disk. Then you pass this analytics to the whole stuff. Then you get another analytic disk. You want to show the exist vector point of the limit of a analytic disk point inside, but we have a lot of trouble because at the this is a pseudo-convex piece, so the exist vector gonna point inside or kind of tangent to that. So we can, with the exist vector tangent to that, we cannot say anything. So we will, so we should fix that. And also the second difficulty is the analytic disk. When you pass it to the limit, there is a singularity. Singularity, we cannot do anything about singularity. So how do we do this? We firstly correct a little bit boundary piece here, just locally around this point, so that this is a less strongly pseudo-convex, but still strongly pseudo-convex. In this case, if you study some, if you do some, after doing some work, you will find actually the angle between the exist vector and the boundary has a lower bound. The angle. So even if you pass to the limit, in limit sense, the exist vector still inside. This is one thing. The other thing is we don't pass all of analytic disk to the singular region. We will do that so that this point is close, 0 point, very close. And then since Hilbert transform is bounded, so we can just do translation. After doing translation, since the exist vector and the boundary has a lower bound, after you doing some after you do translation, you will find it will not change a lot. The exist vector still point inside. Then we have shown this proposition. Oh, this is not okay. This picture. Okay, this is the theorem. I don't want to show that. I don't have time to show you in detail, but you have seen that, right? Okay, that's it. Thank you.